This gray handset from the early 1980s sits next to a standard building brick for a reason. They share almost the same dimensions and weight. Compare that to the thin, buttonless glass slab you likely have in your pocket right now. We usually credit this change to the brilliance of industrial designers, the idea that over 40 years, tech companies simply became more sophisticated at craft and miniaturization. In reality, the physical layout of these devices was dictated by invisible forces. The shape of your phone changed because the radio waves it catches changed. To understand why our hardware looks the way it does, we have to look at how each specific generation, the G, forced the device to mutate to survive on a new kind of network. 1G arrived in the 1980s with a straightforward goal: wireless voice calls. It worked by converting your voice into a continuous analog radio signal and broadcasting it through the air. Constant analog transmission is an energy disaster. Converting and broadcasting a steady voice wave requires a massive, continuous draw of electricity. This energy requirement meant the phone's chassis was mostly battery. You carried a brick because you needed a power plant large enough to sustain a 30-minute call. And since the signal only carried sound, the screen stayed tiny, just enough space to confirm a phone number. The hardware began to shift in the 1990s with 2G. This was the moment the industry moved away from wavy analog signals to digital data. Digitizing the signal allowed the network to carry more than just sound. It could now transmit small, discrete packets of text, creating the first era of SMS messaging. Because users now needed to compose messages rather than just simply dial numbers, the phone's physical body reacted. Handsets sprouted complex T9 and full QWERTY keyboards to act as the primary interface for this new digital data. 2G established the pattern. As the network's capability expanded beyond voice, the phone grew new physical tools to handle that data. 3G launched in the early 2000s, attempting the first real marriage of the phone and the internet. It brought email and basic web browsing to the palm of your hand for the first time. However, 3G was unstable. The network bottlenecked quickly under the weight of images or video, forcing users to browse a simplified, low-resolution version of the web. This chart highlights the shift that occurred around 2010. 4G replaced those narrow, congested pipes with a high-capacity architecture, pushing stable speeds up to 300 megabits per second. With that much bandwidth available, software designers moved toward far more complex tasks: live turn-by-turn navigation, high-definition video conferencing, and data-heavy social media feeds. These apps created a physical conflict. Navigating a map or a video feed requires gestures like scrolling, zooming, and swiping. A physical keyboard, which takes up half the device, became a functional obstacle. To solve this, manufacturers removed the physical buttons entirely. The 4G era demanded a design where the entire front was a reactive surface, leading to the uniform glass slab we use today. The modern smartphone isn't a design trend, it is the physical result of the high-speed data 4G provides. When 5G arrived in 2020, it created a paradox. A 5G phone looks almost identical to a 4G phone from a decade ago. This visual stagnation happened because 4G already reached the limits of human biology. Our eyes can't perceive much more resolution on a small screen, and our thumbs can't swipe any faster. Because the human experience is already saturated, 5G's primary upgrade isn't just raw speed, it is latency, dropping the network's response time to as little as 15 milliseconds. Humans can't feel the difference between 50 milliseconds and 15, but machines can. This near-instant response is designed for remote-operated drones and automated systems requiring precision beyond human reflexes. Looking toward the year 2030, 6G is expected to push this even further. Research suggests terabit speeds running on AI-managed networks that can predict and route traffic before a user even makes a request. At this level of speed and automation, the network prioritizes industrial infrastructure over personal handsets. 6G is built to link satellites, automated robotics factories, and global scientific sensors, systems where the phone is just one small legacy component of a much larger web. These generational shifts are rarely about just letting us watch YouTube faster.
Each G is an engineering response to a specific limitation of the previous decade. We have watched mobile technology evolve from a heavy brick designed for the human voice into a globally integrated, automated network of sensors and data links. The phone didn't just get smaller, it became the interface for a planet-wide machine.